This is the second set of notes for solids, liquids, and so in the previous notes we talked about evaporation. Now we're going to talk about all the different types of phase changes, right? Phase changes are just changing from one state of matter to another state of matter. So solid to liquid, liquid to gas, gas to liquid, liquid to solid, etc. So to undergo a phase change, the substance must gain or lose kinetic energy. And remember, that's essentially the speed that the particles are moving at, right? They're going to move, as they lose energy, they're going to move slower. As they gain energy, they're going to move faster, which usually happens by a change of temperature. Usually, but not always. Okay, so looking at this diagram, this is just trying to give you a visual, right? If something goes from a liquid, right, to a gas, right, what's that called? Evaporation, right? Or remember I said vaporization. Doesn't really matter which one you use. Vaporization is more correct, but it's not a big deal. So what happens when a gas goes back down to a liquid, right? So if there's water vapor in the air, let's say, and it condenses into a liquid, right? What do you call it when you see it on the side of your glass? Right, you call it condensation, and that's what happens on the side of your glass. That if you have a glass with ice cubes in it, right, and your liquid is very cold, these gas particles that are moving around, which might happen to be water vapor, as that particle gets close to your glass, this air right here is really cold, and so as it gets next to your cold glass, it slows down, and then this one slows down, and you start to get condensation on the side of your glass, right? Water vapor is turning into liquid water. Okay, number 3, a solid to a liquid, right? If a solid goes to a liquid, that means, well, everybody hopefully knows that. That means it is melting, right? And then the next one, if a liquid goes to a solid, right, that means that it is freezing. And then we have the ones that people usually forget about or they're not as familiar about with, but when a solid goes to a gas, so it skips a liquid. And this is basically what dried ice is. Dried ice, if you took dried ice and you put it at room temperature, it's never going to get to here. It's going to immediately turn into a gas, and that's, you put it in your punch and you see all of a sudden this kind of fog coming out. That's basically the carbon dioxide exiting as a gas. That is called sublimation. And the last one is just the reverse. If a gas was to go to a solid, then it's called deposition. And you don't see those very often. Okay, 1, 3, and 5. Think of energy as, there's different forms of energy, but kind of think of it as heat. If you have to heat something up, right, then it is going to gain energy. So if you take a solid and you want to make it become a liquid, what do you have to do? You have to heat it up, right? Think about ice. You set it at room temperature, it starts to heat up. That means that it is endothermic. So using this symbol here is what the delta means. The delta means change, and the H means heat. So if there is a positive change in heat, that means it's gaining energy. If a gas wants to condense to a liquid, right, like we were talking about over here, that gas is going to slow down, meaning it's losing kinetic energy, right? So it is losing energy, and instead of endothermic, it is called exothermic, right? And again, now it's a negative delta H, meaning there's a negative change in heat, or it's losing heat, it's losing energy. So our, right, 1, 3, and 5, it needs to gain energy, right, for a solid to go to a gas, for a solid to turn into a liquid, or a liquid to turn into a gas. It needs to gain energy, right? We need a positive delta H, or it's said to be endothermic because it's gaining. Endo is basically in, meaning that that substance is absorbing heat, and that's why those particles move faster, they have more kinetic energy, and so it's able to change to a different phase. And then, 2, 4, and 6, right, are exothermic. So 2, 4, and 6 are exothermic, meaning it's releasing heat into the environment. So heat or temperature essentially is leaving the substance, and therefore the particles are moving slower, allowing them to go from a gas to a liquid, or a liquid to a solid. Okay, heating curves. What this is, if you took a substance and you started heating it, right? Over time, that substance is going to get hotter, possibly. Okay, well, what happens is that if you take, let's say, water, right, that's at negative 100 degrees, it's going to be essentially frozen, right? It's going to be a solid. As you heat it up, that ice is actually going to increase in temperature, and that's what it's showing, right? As you heat up your ice, as you take it out of the freezer, essentially, it's heating, and that temperature is getting hotter and hotter and hotter. Well, the weird thing is, once that ice cube gets to 0 degrees Celsius, and these are all in degrees Celsius, when it gets to 0 degrees Celsius, what happens is, notice that there's this transition here where there's no change in temperature at all. When an ice cube is melting, it's actually not changing temperature. And then once all of the ice melts, then now you have liquid water, right? So this is a liquid substance in here, and that liquid substance, if you, let's say, put it on a stove, it's going to get hotter and hotter and hotter. And once it reaches 100 degrees Celsius, what happens? Those molecules are moving so fast that now the molecules are able to break free, and they are able to evaporate into a gas. And then once you have water vapor, well, that water vapor, you can keep getting hotter and hotter and hotter over time. So let's fill in the blanks here. A solid only, right? We have heat is used to speed up the particles. So that is this section right here, right? That is this line. Heat is speeding up the particles, it's staying a solid. When it transitions from a solid to a liquid, right, energy is used to break the solid apart, which means that, right, we said up here somewhere that it usually happens by temperature. It could happen in other ways, but in this case, right, this is this transition part here where the energy that you're putting in, the heat that you're putting in, is breaking apart the molecules, and instead of causing them to move faster necessarily or get hotter. So if you look back at what we were doing back here, right, this particle here is vibrating, and if it gets hot enough, it can break free from those intermolecular forces, and now it's a liquid that's kind of floating around, right? And then they're all going to kind of do that one after the other, and it's going to transition into a different state of matter, into a liquid. Let's get back to where we were. Okay, next part. Right, we have a liquid. So we're now dealing with this section right in here, right? For a liquid, if you continue to add heat to that liquid, all that's going to happen is the particles are going to speed up, and that means it's going to get hotter. Essentially, the speed of the particles is the temperature. If the particles move faster, that means the temperature is increasing. If they're breaking apart, they're not necessarily moving faster, right? They're just trying to break through those intermolecular forces. So all the energy is used to break through the intermolecular forces instead of just speeding up. So for D, for our transition here from a liquid to a gas, right, as it's moving over from a liquid to a gas, again, the energy or the heat that's being put in is going to break the liquid apart and allow it to break through those that kind of skin at the top of the fluid so that it can become a gas. And then the last part, right, if you continue to heat the gas up, it is only going to make the particles move faster. And you could have the reverse of this situation, right? If all of a sudden you wanted a substance to cool down, right? If all of a sudden instead of heating, it was cooling, right? You put it, you take your, let's say, whatever it is, you take some gas and you put it in a freezer. What's going to happen is that gas is going to decrease in temperature. Then it's going to right, condense into a liquid. Then that liquid is going to get colder, which is really where something's normally at when you put it into a freezer, right? And as that liquid gets colder, now it's going to freeze and become a solid, and now your solid can get colder and colder and colder. Which is right what I was just explaining here in this cooling curve. So it says, label the graph with S for solid, L for liquid, and G for gas. So we know that at the hottest temperature, it's going to be a gas. In the middle state, it's going to be a liquid, right? And then down here, it's going to be our solid, assuming again this is water. Our solid is going to be getting colder and colder and colder. It says put GL for a gas liquid, and that's what's happening in this transition state, right? The gas is condensing into a liquid at this point. And then the other one, it says LS for liquid solid, right? That's this process where our liquid is freezing into a solid, which I put, right, freezing and solid already in there. Okay, last thing, a phase diagram. This can be a little confusing. So substances can be solid, liquid, or gas depending on the pressure, which is shown over here on the y-axis, right? And it's in ATMs, and the temperature, right, which is shown here on the x-axis. So all this is trying to tell you is basically you have to look at the combination of both. 1 ATM is a normal atmospheric pressure. So if you look at this, right, and you're talking about water, when water is at the atmospheric pressure, right, usually at 0 degrees Celsius, it's a solid. And as it heats up, right, it's over here as a solid, and as it heats up and it gains temperature, what happens? It becomes a liquid. And as that liquid gets hotter and hotter and hotter, when that liquid gets to 100 degrees Celsius, then it turns into a gas. Well, that's at atmospheric pressure. If you go up in altitude, now all of a sudden you're at Flagstaff. Oops. You're at Flagstaff, right, where the atmospheric pressure is less, right, now all of a sudden water is going to boil at a slightly higher temperature, right? It's not going to be, or sorry, water is going to melt into a liquid at a slightly higher temperature. And same thing, right? If we're following this over, water is going to boil at a temperature less than 100 degrees, which is why you'll see like high altitude cooking directions, because things are cooking differently at higher altitudes. So this whole entire thing is just trying to show that as far as melting, freezing, condensing, all of those things, it's dependent on pressure and temperature, and you need to look at it. This triple point here is what that's saying is at that point you would have something that would be a solid, a gas, and the liquid all at the same time. If water was at 0.006 atms at 0.01 degrees Celsius, you would have all three things present at once. You would have water vapor, ice cubes, and liquid water, and nothing would be changing from one to the other. So let's fill this in real quick, right? Triple point is the temperature and pressure where all three phases exist. The line that divides each section is the exact temperature and pressure where both phases exist, right? At 0 degrees Celsius, what's happening? You have ice transitioning into water or liquid water, so both phases exist, right? Or if you have a pot of water at 100 degrees Celsius, right, at standard pressure of 1, what's happening? Your liquid is turning into a gas, or it could be possibly turning back into a liquid, depending on which way it's going. So hopefully those notes help you out and you have a little better understanding on solids, liquids, and gases.